So in today's video, we're going to be looking at section 11.11 in the Calculus Early Transcendentals book, and this one is the 6th edition by James Stewart. So chapter 11.11 is the application of Taylor polynomials. So before in 11.10, they just go over what a Taylor polynomial is. So I'll just give a recap of what that is. So in mathematics, we have a Taylor series, and the Taylor polynomial is basically just an equation that is a representation of a function as an infinite sum of terms that are calculated from the values of the original function's derivatives at one single point. So we have one point, and that point is usually just defined as like point t, and that point is where we're going to be taking the function's derivative and use it to find a function to calculate that graph. So if we get started right here, we can just look at what a Taylor series is. So it's defined as f of x equals the summation as n equals 0 to infinity of f to the n power of a divided by n factorial all times x minus a to the power of n. Okay, so I've already set up a problem where we have the equation f of x equals the cube root of x, and we're trying to find the second degree Taylor polynomial of this function at a equals 8. So I already set up that we have f prime of x equals 1/3 x to the negative 2/3, and then I have f double prime and f triple prime. And then I also have their values when x equals 8 over here. So if we're going to find the Taylor's second degree polynomial of this equation, I already have it written out right here. And what I'm going to do for this video is find the error. So if we want to find the error between when the approximation is between 7 and 9. So between 7 and 9, the error for this is going to be defined by an equation, and so we're going to use the equation of the absolute value of r of the n of x equals or is less than or equal to the absolute value of f to the n plus 1 of x times the absolute value of x minus a to the n plus 1, all divided by n plus 1 factorial. So if we have this, we're going to just plug in a few things. So in the first one, we went to n value of 2. So our n value is always going to be 2. So we have the third derivative of f of x, and we need to maximize that on the interval 7 to 9. So our third degree of f of x equals 10 over 27 times x to the negative 8 over 3. So if we want to maximize something that is to a negative degree, we're actually going to use the smaller number, because the smaller number is going to give us a larger number overall because the denominator is going to be smaller. So we're going to use this when x equals 7. And then if we want to maximize x minus 8 to the third power as well, we can use either 7 or 9 because both values are going to give us an ending value of 1. But yeah, because it's in absolute values. So both of them are going to give us an ending value of 1. And then on the bottom we have n plus 1 factorial, which is just going to be 3 factorial. So if you plug this right here into your calculator, you're going to get 0.0021. So overall, r of 2x, the absolute value of this, is less than or equal to 0.0021 times 1 from this maximization, all divided by 3 factorial. And if you do this, what you're going to get is 0.0004. So that basically means that our error is 0.0004. So the approximation in this part of our Taylor polynomial is accurate within 0.004. Now, if we had a graphing calculator and we would have been able to graph this, we would have found that it was going to be that the absolute value of r2 of x was less than 0.000 0.03. So that's still a very good approximation by just doing the mathematical side instead of actually looking at a legit graph. Because doing an actual graph and using the calculator is obviously going to be a more accurate answer, but if we came between 0.0001, which is a very good thing to be within. So overall, some of these problems are going to give you the problem backwards, and they're not going to ask what the actual error is. They're going to ask how many terms you would use to find the error within 1/1000th or something like that. So they would ask you what the error would be between something like this, and you would have to set it up as r of n of x, and then you're going to find the value of n. So you would basically just do something like this, and then you would plug in r n of x as this part of the actual equation, or you could just set this part of the equation equal to this part of the equation. So there you can go back and forth between finding the actual error in each of the equations, or actually just finding the value of n to find the error within a certain bounds. So to finish up our video, we're just going to look over a general problem that we can just use for all Taylor polynomial problems, and it's just a very generalized problem to ask. So they're asking us to basically just find the second degree Taylor polynomial at x equals 2 to approximate f of 1. And they just give us f of 2 equals 3, f prime of 2 equals -5, f double prime of 2 equals 4, and f triple prime equals 6. So right off the bat, we can just already find the Taylor polynomial at x equals 2, because it's a really simple just plugging it into our equation. So our equation is just going to give us f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 times x minus 2 all squared over 2 factorial. And that will give us the second degree, so we don't have to go any further. And this is equivalent to the Taylor second degree Taylor polynomial of x at x equals 2. So if we simplify all of this, f of 2 is just going to give us 3 plus our x prime of 2 times x minus 1, and our x prime of 2 is -5, so it's going to be -5 times x minus 2, all plus our f double prime of 2, which is 4, times x minus 2 squared over 2 factorial, which is just 2. So these two can cancel out, and this will just become a 2. So we can rewrite this as our second degree Taylor polynomial of x equals 3 minus 5 times x minus 2, and -5 times -2 is just going to give us 10. So we're going to have our 13 minus 5x plus 2 times x minus 2 squared. So we don't need to factor out the entire thing, but if they want us to find the approximation at f of 1, all we're going to do is plug in 1 for x. So we're going to get 13 minus 5 plus 2 times -1 squared. So that's just going to give us 13 minus 5 plus 2. And we can just find that, and that is going to give us 10. So our overall answer for the second degree Taylor polynomial at x equals 2 to approximate f of 1 is going to give us 10.